Hello everyone, this is the time of the class of ECE317 Digital Signal Processing. Welcome. ECE317, this is for the 7th week, Friday's class. Alright. Today we will consider the inverse Z transform. Inverse Z transform. We have several cases. In each case you can use different method. So let me start. The first case, I use example to explain. The first case, suppose we have capital X of Z. For example, I have 3Z plus 2 plus 3z to negative 1 and minus 4z to negative 4. Suppose this is x of z. It is a summation of some terms with power of z and the coefficient before the z. So this one, you go back to time domain, they are just those coefficients. We have x of n, it will be 3, 2, 3. Okay, here you see z to negative 1, z to negative 4. We do not have z to negative 2, z to negative 3. So actually here we need 2 zeros for those two terms. And then negative 4. Alright, so this is the answer. Indicate here n equal to 0. This constant according to z to the 0. Z to 0. Right? Yeah, that's it. This is just by definition. Just by definition. Alright, it's the most simple case. And the second case, we can by table directly. By table directly. I'll show you the example to explain it. Suppose x of z equal to 1 over 1 minus 1 half z to negative 1 and z larger than 1 half. Okay, you check the table. You will have x of n, which is 1 half to the n u of n. It's just directly from the table. Alright, this is also simple. And the third case, a little bit complex. You cannot use the table directly, and you need to make some changes. You also use an example to explain it. X of z equal to like 3 minus z to negative 1 over 1 minus 1/6 z to negative 1 minus 1/6 z to negative 2. And our c will be what? I have a 1 half, I have a 1/3. It's larger than 1 half. Alright. Okay. So this one you cannot use table directly. So you have to make some change. The idea is you rewrite these in some simple terms, and each simple term looks like this. So you can find the inverse Z transform from the table, right? And okay, to do this, we need to separate the denominator as a multiplication of two factors. So this one I can write as 1 minus 1 half z to negative 1 and 1 plus 1/3 z to negative 1. Here's 3 minus z to negative 1. Right? You see the denominator. 1 is 1. 1 times 1, you get 1. 1 times 1/3 and 1 times negative 1 half. These are the coefficients before z to negative 1. Right? So it's a negative 1 half and positive 1/3. You add them together, you get a negative 1/6. And square term is a multiplication of these two. So it's 1/6 times z to negative 1. negative 2. Right? Okay, now we suppose this one equal to a over 1 minus 1 half z to negative 1, and b over 1 plus 1/3 z to negative 1. Here, a, b, we do not know what are these right now. We will find them later. Okay, and this method we call this is the partial fraction method. Partial fraction. You write this is a single fraction, a complex fraction, right? Now I write as summation of some part, right? Some part. Each part is a simple fraction. Yeah. Okay. Now times 1 minus 1 half z to negative 1 and 1 plus 1/3 z to negative 1. This is the denominator of the whole fraction. We times these on both sides. This side, right? These two are same. I times these on here, I get 3 minus z to negative 1. And equal to, I times these on here, a and b term. In a term, the denominator 1 minus 1 half z to negative 1 can cancel with this one, right? So we only have 1 times 1 plus 1/3 z to negative 1. And the second term, I have b times these, and times these, b over these, and times these. So 1 plus 1/3 terms erased. So I have b times 1 minus 1 half z to negative 1. Alright, at this point, you still have two ways to solve it. The one method is you pick some special value of z, plug in, right? This is a function of z. So they were equal for any z. You pick a special value of z here, then you can find a and b very easy. So let z equal to 1/3, negative 1/3, negative 1/3. You see this one, 1 plus 1/3 z to negative 1, z equal to negative 1/3. It will be what? It is 1 plus 1/3 times negative 1/3 inverse, right? So these two cancel. This is divided by 1/3, right? 1/3 divided by 1/3. Only one negative left, so it's 1 minus 1, you got 0. Okay, so you plug these in here. We have 3 minus z to negative 1, it is negative 3, plus a times these, we got 0, equal to a times these, you get 0, and b times 1 minus 1 half z to negative 1, z to negative 1 is negative 3. Alright, so this is b times 1 plus 3 over 2, which is it's a 2 here. It's a 2 plus 3 is 5. b times 5 over 2. And this side is 6, right? 3 minus negative 6, I get 6. So we have b is 6 times 2 over 5. Right? I move 5 to 2 that side, and then reverse. I get this one. This is what it is. Let me times 2. This is 24 over 10, right? It's 2.4. I get this one. And then a. I can use the same way to find a. Let z equal to, now let z equal to 1/2. Then we have 3 minus z to negative 1 will be 2, right? And equal to a times 1 plus 1/3 times z to negative 1, that is 2. And b times 1 minus 1/2 z to negative 1 is 2. Right? So this is 0. Okay, I get a times 3 over 5. This is 1. Okay, so A is 3 over, this is 5 over 3. A is 5 over 3. A times 5 over 3 equal to 1. So A is 3 over 5, the 0.6. Alright. So we can have A and B by this way. Alright. And another way, to determine A and B, we check the coefficient on both sides. Here you have constant 3, and this side you also have constant A and B. So we have 3 equal to A plus B. This is the coefficient of 1 on both sides, right? Coefficient. This side is coefficient of 1 is 1. Actually, it is a z to 0, right? It is 3, and this side is A plus B. And negative 1 equal to is a 1/3 A minus half B. This is a coefficient of z to negative 1. Got it? And z to negative 1. So we have equation, right? We have equation. Then we try to solve this equation to determine A and B. Okay, so 3 equal to A plus B, so A equal to 3 minus B. Then I plug in the second, negative 1 equal to 1/3 A, now it's 3 minus B, minus half B. So it's negative 1 equal to 1, right? 1/3 times 3. And minus 1/3 B minus 1/2 B. So this is 1 minus, this is 1. 1 minus, this is a 5 over 6 B. So I move this negative 5 over 6 to left. I have 5 over 6B, right? I've changed the sign. And negative 1 to the other side, I get positive 1. And here's 1, so it's 2. Alright, so B equal to 2 times 6 over 5. Okay, I got 2.4 again. And then B is 3. A is 3 minus B. So we have A is 0.6. Right. Okay, we get same answer. Same answer. Yeah, you can use either way to determine A and B. And sometimes you can mixture. For example, here, when you get B is 2.4, you also know these, right? You observe the equation, you can have these. These are very simple. 3 is A plus B, and B is 2.4. Then you can claim, okay, A is just 0.6. You don't need let Z to some other value to determine A. All right. Okay, this is the case. And here, when we try to separate the whole fraction, the original fraction, into small pieces, into simple pieces, sometimes we will have some square terms or even cube terms. Let me see. Example, I have x of z equal to 1 minus 1/3 z to negative 1 square times 1 minus z to negative 1. Here, okay, here just 1, alright. Yeah, we have the inverse terms, doesn't matter. The main point is for the denominators. Then, this time, how to separate them? Now we suppose x of z were equal to, I still have these two factors, right? One is 1 minus z to negative 1. One is 1 minus 1/3 z to negative 1. So I have A over 1 minus z to negative 1 and B over 1 minus 1/3 z to negative 1. However, only these two is not enough. because here you have a square term. Then you need to add a square term 1. 1 is a square term here. 1/3 z to negative 1 square. Here's a constant c. If you do not have these, when you times these two together, you add these two together, the result, denominator only contains the multiplication of these two factors, right? You add these two fractions together. What will be the new denominator? There will be just this one times this one, but no square. So make sure you want this square, so you have to have another term. You have to have this one. And for this one, we can still have it from the table. Oh, I forgot one thing. I haven't finished, sorry. I got A and B. I got A and B, right? A and B. Oh, let's go back, and we discuss this later. A and B, right? A is x of z is go back to previous example. X of z is a over a over 1 minus 1/2 z to negative 1 plus b over 1 plus 1/3 z to negative 1, and our c is z larger than 1/2. Alright. And a is 0.6. This is 2.4. So we have x of n or equal to, you see, z larger than 1/2, and here is 1 minus 1/2. So this is just exactly the same thing in the table. This will be a, which is 0.6 times 1/2 to the n z to u of n. And second is b, 2.4. Okay, here's a 1/3. 1/3, you check the table, you want z larger than 1/3. Right? You want this one. And we only have these. Can we have these? I will say yes, right? It's larger than 1/2, of course, it's larger than 1/3. So this one, in the problem, this is 1/2. And you check the table, it satisfies this condition. This RC is larger than 1/3, right? So we can use this one. Use this RC and this function in the domain. Then we go back to time domain. This 2.4 and negative 1/3 to the n u of n. Alright. Yeah, I forgot these. Okay, now let's go back. This is prove this. Okay, now we go back to this one. We still need to find the A, B, C, right? So we do the same thing. We multiply this one, the denominator, and both sides. Then we have 1 equal to, this one is a times 1 minus 1/3 z negative 1 to square. And second term, it is a b times, okay, I cancel one of it. I have another 1 minus 1/3 z to negative 1. And 1 minus z to negative 1. Right? And the last one, c, the square term canceled, right? So I have c times 1 minus z to negative 1. Okay, so we choose like a z equal to 1. Z equal to 1. This is 0, right? This is also 0. So we have 1 equal to a times 1 minus 1/3 squared. Z to negative 1 is 1. Yeah. So this is a times 2/3 squared is a times 4 over 9. So we have a, which is 9 over 4. Okay, this is a. And another number we can use here is z equal to 1/3. So let z equal to 1/3. Then we have this side is still 1, right? No matter what is z, this side is just 1. So 1 equal to a times 1 minus 1/3 times 3 with square, and b 1 minus 1/3 times 3 and 1 minus 3, and plus c 1 minus 3, z to negative 1. This is 3. Alright, this is 0, this is 0. So we have 1 equal to negative 2c. So we get c is negative 1/2. Alright, yeah, you get this. Then what is we have a, we have b, we have c. Now how to determine b? The special value, this is 1 and 1/3, we already used, right? So we cannot make them equal to 0 anymore. So we can pick any value, like let z equal to 1. Right? Just let z equal to 1. Then we have 1 equal to a times, I use negative 1, okay, negative 1, z equal to negative 1. So a is 1 minus 1/3 times negative 1 squared, plus b 1 minus 1/3 negative 1 squared, and 1 minus negative 1, plus c 1 minus negative 1. Alright, so 1 equal to this is 1 plus 1/3, so it's 4/3 square a, right? And the b, this is also 4/3, right? 4/3. So b times 4/3, this is 2, and c times 2, and we know c is negative 1/2. A is 9/4. So 1 equal to, this is a 4 square over 9. 9 cancel. 4 square and 4 cancel 1. So I have 4 left. And this is a b over b times 8/3. And b is 1. I want to find b. Okay, so 8/3b. And c is a negative 1/2, which is minus 1. Okay, so we have 8/3b were equal to 1 plus 1 minus 4, right? 1 plus 1 minus 4, so it's a negative 2. Okay, I get b equal to negative 3 times 2/8, which is negative 3/4. Alright, so we have ABC, right? We have ABC. You can also try to solve equation. You compare both sides. You check the coefficients of 1, z to negative 1, and z to negative 2, right? Z to negative 2 and z to negative 1. You check the coefficient of both sides. Then you can have 3 equations. You solve those 3 equations, then you can find ABC again. However, in my sense, actually, I feel so the 3 equations will not be easier than this way. You just choose some special value, then you can find the sum of A, B, C easier, and the last one, you can also, because A and like here, A and C are already have, right? So you pick some value, then you can have B. Alright, now we can have our answer. X of n equal to, okay, A is 9/4, and A is a coefficient of what? A is here, but I didn't give the RC. I didn't give ROC. So what would be the ROC? So here I don't have ROC. That means several possibles. We can try to find all the possible ROC, right? Depending on the ROC. So we can have three cases. The first ROC, we just use the larger side. We suppose Z larger than something. Larger than what? I have 1 and 1/3. So Z should be a number larger than 1 and 1/3. So larger than 1. In this case, larger than 1, you use the table larger one term. That will be, I just put it here, 1/3 to the n u of n. Oh no, a is 1 over z, sorry. 1 minus z inverse. A is a coefficient before 1 over 1 minus the inverse. So it is just u of n. It's a u of n. And the second is b. B is what? B is negative 3/4. B is negative 3/4. Right? B is negative 3/4. So B is negative 3/4. And the B is a coefficient over 1 minus 1/3. So this is a 1/3 to the n u of n. And last one, I have square. You need to check table. Can you remember that? I can't remember. I can't remember that. Let's go to the table. I have table. The transform is n plus 1 something. Square this one. Do I have square term? Oh, I have square term with z to negative 1. This is not good. But actually we have, we go to this one, Fourier transform. Fourier transform. In Fourier transform, we have the square term. Yeah, this one. You see? This one. When this a is smaller than 1, absolute value of a is smaller than 1, in z domain we also have this. Just replace this exponential power by z. So z to negative 1 here. Alright. So you can use this. Use this. You can use this. So this is n plus 1. Let me copy it. It is n plus 1 times a to the n. What is a right now? A is 1/3 and u of n. Right. It's 1 minus a times z negative 1 to square. And here's n plus 1 times 1/3 n. Okay. Just this one. I copy it again. Alright. This is for the RC like this. If RC this one. And xn, another case, I use a different RC. Here I have these values, 1/3 and 1, right? 1/3 and 1. Yeah. This is 1/3, this is 1. So the first one I use larger than 1. Now I consider smaller than 1/3, right? This is smaller one, even smaller than this. If RC is z smaller than 1. Smaller than 1, then we have, you see, this one. Smaller than 1, we still have this one will give us negative u of negative n minus 1. Okay, so I just plug in. This is a negative. Coefficient is still 9 over 4, but this is a negative u of negative n minus 1. Alright. I copy it here. I copy it here. This 1 over z to negative 1 in time domain is negative u of negative n minus 1. Alright. Yeah. And the second term is b. b is negative 1/3. 3/4, sorry. 3/4. And the denominator is 1/3. And here you see z is smaller than 1. Oh, yes, smaller than 1/3. Smaller than 1/3. Smaller than the smallest one. I just said this z should be smaller than 1/3, but when I write, my hand write 1 here. Sorry for that. So z is smaller than this. Smaller than 1/3. Smaller than 1/3. So this is also negative. So I have a plus here. Then it's 1/3 to the n and the u of negative n minus 1. Check the table. Right here. Z is smaller than a. For this one, go back to time domain, still an times u something. But inside the u, the time index is negative n minus 1. And before the power of a, you need a negative. Right? Yeah, this is just I put it here. Alright. And the last term is still this. But change this to be negative n plus 1. Change this to negative. So negative n plus 1, 1/3 to the n u of negative n minus 1. That's it. Okay, now you can compute. For all of them, they are larger than 1, and all of them are smaller than 1/3. These two different ROC. The result, the coefficient, just change the sign. Okay, change the sign. And then the main part of this will be same. Right, here's a 1/3 to the n, 1/3 to the n, 1/3 to the n. This is 1. Right, this is n plus 1 times 1/3 of 1/3 to the n. And then the u. For u, the index for the positive one, this is n. For z larger than 1, this is n. For smaller than 1/3, this is a negative n plus 1. Alright. Okay. Now we have the third case. If ROC is z between 1 and 1/3. So it's 1/3 smaller than z, smaller than 1. Between these two values. Yeah, the whole thing is 1, the 1/3. The case 1 is this, case 2 is this, case 3 is here. Yeah, between 1 and 1/3. If RC is this, then we have x of n equal to, for the first term, a over 1 minus z to negative 1. Now is z smaller than 1. Right? Smaller than 1, so I use a negative of it. A is 9/4, and u of negative n plus, minus 1. And the second term, now is z is larger than 1/3. Larger than 1/3, so this is a negative 1/4. This is b times 1/3 to the n and the u of n. And plus n plus 1 times 1/3 to the n and the u of n. Alright, so we have these three cases. And here we have something I need to mention. Here this 1, here the coefficient is 1, right? 1 times z to negative 1. Here is 1/3 times z to negative 1. Now here is also 1/3 times z to negative 1. These three numbers, we call them the poles of x of z. Because if you plug in z to negative 1 equal to 1, you get 0 in denominator. Oh, this will give you infinite, right? Like a over 0. Similar, if z equal to 1/3, then this is 1/3 divided by 1/3, you get 1. and 1 minus 1, that's 0. So you have b over 0 again. Yeah, this is similar. So we call these 1 negative 1 third. They are the poles of x of z. 1 third are poles of x of z. This is just for this example. Different example, the poles might be different. Of course, usually different. And this one, this pole is just order 1. But this one is order 2 because we have square on it. We have square on it. The multiple poles. We have square on it. Alright. So and the ROC, you just put all the poles. You start from 0, and put all the poles. Then each segment is a possible ROC. Yeah. Smaller than 1 third, larger than 1, and between 1 and 1 third. Right. Each segment, these poles, the poles gives several separated the not whole real number. It's a positive real numbers as a segment. Then each segment according to one possible ROC. Alright. So like here, because absolute value of z, so must be positive. We only have positive. Yeah. ROC. Possible ROC. The poles separate from 0 to infinite to several segments. Each segment give one ROC. Alright. Yeah. Each element give ROC. If you have a function like you have 10 poles, then how many possible ROCs what do you have? You have 10 poles. Now you will have 11 possible ROCs. That's a lot. Yeah. Of course, in the homework, in the exam, we were not working so much. You know the idea, that will be fine. Alright, you know the idea. You know several poles. Okay, then you have to choose the possible ROCs. If ROC is given, then you just use that ROC. If ROC is not given, you need to check which one is which one. Alright. Okay, this is one case. I forgot the number. 1, 2, 3, 4. So first one is by definition. Second one is from the table directly. The third one we need a partial fraction. Okay, third one. Now we consider the fourth. This is 4 or 6? I think this is 4. That one is 6, right? That one is 6. Anyway, the 4. Okay, the fourth case, I also use an example to explain. X of z equal to 1 minus z to negative 1 minus z to negative 2 minus z to negative 3 over 1 minus z to negative 1 square. Then what is the, okay, I want RC is z larger than 1. Okay, suppose this is given. Now how to find the inverse z transform, how to find the time domain signal. Here you see, the thing is denominator has order 2. Denominator order 2. Numerator order 3, right? Order 3. So we have more order in the numerator. This is not a primer fraction. Not the primer fraction. We want the previous case we consider. Actually, we need this one is a primer fraction, but now it is not. So we need to do some change. And here actually we can work in two ways. X of z equal to 1 over 1 minus z to negative 1 with square, and minus z to negative 1 and 1 minus z to negative 1 square, minus z to negative 2, 1 minus z to negative 1 square, and minus z to negative 3 over 1 minus z to negative 1 square. Then we have what? We have x of n. You see the first factor, first fraction. This is just n plus 1 times u of n, and just like this. Okay. And the second one, I have z to negative 1 here. Okay, we can have these by a property of the transform. You can see. This is Fourier transform. Yeah, it's in the lower part. It's here. You see, it times z to negative n0 in front of x of z. That means you have a shift on x, and RC just the possible addition or deletion of the 0 and or infinite. So it doesn't matter what it is. You just think this is a shift by n0. Alright, shift by n0. So this is just a shift by let's go here. So it is shift of this one by 1. So minus, right? This is minus, so here's a minus. And n plus 1, n will replace by n minus 1 plus 1. And u of n is replaced by n minus 1. You replace all the n by n minus 1. Alright. And the third term, similar. Now is a shift by 2. So it's a replace all of n by n minus 2. U of n minus 2. And last one, shifted by 3. Right? So this is a minus n minus 3 plus 1. And u of n minus 3. Alright. And we do a simplify. It is n plus 1 times u of n minus n times u of n minus 1. And this is a minus 2. Minus 2 plus 1 is n minus 1. And u of n minus 2. And the last term is n minus 3 plus 1 is n minus 2 times u of n minus 3. Alright. Okay. This is one method. This is one method. The second method, we divided. This is fraction, right? We divided, so we can have some. This is fraction, right? We can move some terms without a fraction, move them in front. So this is a B. The second method, method B. So 1 minus z to negative 1 minus z to negative 2 minus z to negative 3 divided by 1 minus square. Let me times. It is 2 of z to negative 1 and plus z to negative 2. Okay, this is denominator. And I put a 1 here. I have 1 minus 2 of z2 negative 1 plus z2 negative 2, right? Same way just the fraction, right? Divided. So this is negative 1 minus negative 2. So I get 1 of z2 negative 1, right? Here's a negative 1 minus a positive 1. I have negative 2, z2 negative 2. And here's still negative z2 negative 3, right? Okay. I wrong order. I need to reduce the numerators order. So I need to write this way. I put negative z2 negative 3 in the front, negative z2 negative 2, negative z2 negative 1, and plus 1. And this side I also use higher order in front. So this is z to the negative 2 minus 2 of z2 negative 1 and plus 1. Yeah, we have to write it in this way. By this way, we can reduce the order of the numerator. Okay, I put negative z2 negative 1 here. So I have negative z2 negative 3, right, times these two, and plus 2 of z2 negative 2 and minus z2 negative 1. Okay, this cancel, and this is negative 1 minus 2 is negative 3, z2 negative 2, and they cancel, and plus 1. Now I times negative 3. So I have negative 3 z2 negative 2 and plus 6 times z2 negative 1 and minus 3. Okay, so first term cancel. This one is a negative 6 z2 negative 1 and 1 minus 3, I get positive 4. Okay, we're done. This is power is negative 1, order is negative 1. You cannot put anything here. So we have x of z equal to negative z2 negative 1 minus 3 and plus negative 6 z2 negative 1 plus 4 and z square minus z negative square minus z negative square minus 2 of z2 negative 1 plus 1. The next one, we can use partial fraction. And this one, in time domain according to negative 2 and negative 1. Negative 3 and negative 1. Right? This one according to this, not x. X is the whole thing. Just this part. This part according to this one. Right? This part give us this one. Two numbers, negative 3 and negative 1. Two numbers. Then the result will be this one plus, you by partial fraction you can find this one. Then you put them together. I will not do it here. If you're interested, you can try it by yourself. All right. Yeah, to compare what's the difference. Okay, then we have another last method. The long division. I also use an example to explain it. Okay, just x of z equal to 1 over 1 minus 1 half z2 negative 1 and z larger than 1. Okay, and we perform long division. 1 over 1 minus 1 half z2 negative 1. I put a 1, I have 1 minus 1 half z2 negative 1, I have positive 1 half z2 negative 1, right? It is 0 minus this, I get this one. and plus 1/2 z to negative 1. I have 1/2 z to negative 1 minus 1/4 z to negative 2. So here is 1/4 z to negative 2. And here is plus 1/4 z to negative 2. Right? And then we know we use the first method. This is a summation of some terms with z to some power. So we have x of n in time domain, x of n. There will be 1, 1/2, 1/4, and you can imagine it will be 1/16 and so on. And here is n equal to 0. Right? You can work like this. But here you have to mention this is for n larger than 1. Then here is 1 minus 1/2 z to negative 1. Here is also put 1 in the front. 1 in the front. Okay. So the order is the order decreasing, right? Order 0, order negative 1, order negative 2 is decreasing. Yeah, both order decreasing. And if RC is large, I still use this one. RC is smaller than 1. Smaller than 1. Then I need to put them this way. Okay, here just 1, so we do not have any choice. But this side you need to put 1/2 in the front. Plus 1. You need to put this in the front. Then here you need to put 2z, right? You need to put 2z. Then by 2z here you get 1. Negative 2z. Negative 2z you get 1. And this is negative 2z. So here is a positive 2z. And then minus 4z squared. So here's a 2z, right? I times this 2. So 4 and the 2 will cancel. Negative, negative is a positive. And z squared and z negative 1. So I get 2z. Right? And the second term is a plus, minus 4z squared. So I get 4z squared. And then minus, now I need 8z cubed. So I have 4z squared plus minus 8z cubed. I get 8z cubed. So I can keep working like this. Then we know x of n will be the coefficients. Okay, here the order you see is z squared, z cubed. So this is according to, because xn, z to the n, right? Negative n, right? This is term in x of z, right? Term in x of z looks like this. So here should be negative n, and this is a z. So this one according to negative. So I have at least negative 8, negative 4, negative 2, like this. And this one according to n equal to negative 1. So you need to write this. Actually this is as same as negative. There will be 1/2 to the n and the u of negative n minus 1. Yeah, you can check. You can check. They should be same, step by step, element by element. You can find they are same. Alright, that's all for today. Sorry I used a little bit longer time, 4 minutes. Okay. Anyway, that's all for today. See you next time. See you next week. So have a good weekend.